This section and the following section will deal with applications of double integrals. Here in this section, we'll try to find the mass and center of mass of a planar lamina, and then we'll apply double integrals for probability and mean values. Let's begin with density and mass. The lamina is occupying a region D in the xy axis. Then its density is defined as in this equation. We first consider the subregions, and delta M is mass and delta A is area of each small rectangle. When we take a limit, delta A approaches 0, then we can find local density. So the mass of lamina over the region can be approximated as in this equation. For each subrectangle, we find rho, the value, density. So it is a kind of height, and delta A, that's area of a small rectangle. By taking the limit and Mn approaches infinity, we can get the total mass. So it's the limit of Riemann sums, and in integral we can write in this way. Okay. Find the mass of a triangular lamina with vertices. We have 3 points. And given that the density at xy is 2x plus y. Okay. For this problem, what we have to do is to find the mass. And mass is defined a double integral over the region of the density. Right? Okay, so let's try to visualize the triangular lamina. There's x direction. Now that is y direction. Okay, and first point is 0, 0. And second point is 2 and 2. That is 2 and that is 2. So here. And the final point is 0 and 4. That is 4. So we have 3 points. If we connect them, then that's the triangular lamina. Okay. So we have to access this domain systematically. Now, all to integral can be x direction. So x is moving from 0 to 2. Now, for each x, this is a bottom y, that is a top y, right? So the y is moving from here to there. This bottom y is y equal x, right? That's 45-degree angle. Okay, that one, again, the slope is -1. And this point is y equal 4 minus x, right? Okay, so for each x, bottom y is x, top y is 4 minus x, and the integrand is 2x plus y, and y direction first, and x out integration. Okay. Here, from 0 to 2 is y independent. So therefore, this first one, we have 2x, and now length is 4 minus 2x. From the second one, its antiderivative is half y squared. We are evaluating from x to 4 minus x. After getting this one, we can get x integration. Okay. from here, from 0 to 2. Okay, let's rewrite one more time. There is 8x minus 4x squared plus half of now 4 minus x squared and minus x squared. Okay, and dx. Okay, from 0 to 2, 4x squared minus 4, we have x squared minus x squared. So no contribution from here, minus 4x squared. Right? And then for x terms, we have 8x half. In fact, minus 8x, half is minus 4x. So 8x. So that is now plus 4x. Right? And then for the constant term, 16, half, that's 8. And x integration. And from here, minus 4 over 3x cubed plus 2x squared and plus 8x from 0 to 2. If you evaluate it, then that will be 40 over 3. Okay, that's the final answer. We have a definition. The moment of a particle about an axis is the product of its mass and its direct distance from the axis. So that is the definition. And through these first moments, we can define the center of mass, x hat, x bar, and y bar. If you follow this line, then it's a little bit confusing. So let's try to focus on only this one. Now, the center of mass, the x component is here 1 over m and double integral over the x times the density. Okay, so in a sense, now x is averaged along with the density. The total density integration is mass, so that it is a kind of averaging along with the density. So it's x average over density, and y bar is y average over density, right? So just you have to understand this too, okay? Okay. Find the center of mass for the triangular lamina with vertices. So we have the same problem, but we have to find now center of mass for the same problem. And so your x bar must be 1 over m double integral over the x rho, and y bar, okay, that must be 1 over m and double integral over the y rho, right? Okay, so let's do it. And okay, 1 over m, we can apply this one later on. So let's try to get only here double integral over the x rho, which must be, already we know how to access the domain D. Here x is moving from 0 to 2 for each x, bottom y, top y, so that we are accessing the domain vertically without missing, without duplicating. Okay, so we have to access the point once and only once. Okay, that is from 0 to 2, and bottom y is x, top bar is 4 minus x. And x times 2x plus y, so that 2x squared plus xy, right? And dy and dx. Okay. For this one, now from 0 to 2, and y directional integration. Okay. Now, that one is y independent. So that 2x squared, the length is 4 minus 2x. And from second one, we have now half x and y squared. For this y squared, we have to evaluate from x to 4 minus x. Right? Then here, okay, now we'll rewrite again from 0 to 2. Okay, this is now 2x, okay, let's try to expand. That's 8x squared minus 4x cubed, and then here half x and y squared. So half x and 4 minus x squared. Okay, let's put here, and minus x squared. Okay, now dx. Algebraically, it's a little bit complicated. However, it's doable. Okay, from here, from 0 to 2, x cubed, we have only this one. We have x cubed here, but cancelled. So minus 4x cubed for x squared. Now we have 4, and again 8 in now minus 4, so the plus 4x squared. And how about x term? And that is now 16 and half x, so that 8x. Okay. And from here, there's a minus x to the 4 plus 4 over 3 x cubed and 4x squared, and from now 0 to 2. Okay, you can get it from now on quite easily. And after getting this value, let's say that is star, then here we can conclude x bar must be star over m is 40 over 3. So that will be the final answer. The exactly same way for this term, if we focus on only this integral y rho, then that is now from 0 to 2 x directional movement from 0 to 2, and bottom y is x, top y is 4 minus x, and y times rho. So that is 2xy plus y squared and dy dx. You can get integral, iterate to the integral. First you do this one, and then later on x integration. After getting a numeric value, now again divide by m, then you can get final answer. Already here answer given, so that after finishing the calculation yourself, try to see if your calculation is right. Okay. Now we'll apply the double integrals for probability. we have a recall here. The probability density function f of a continuous random variable x is a function such that at every point the function is non-negative and the integral over whole real line must be 1. And if we want to get the probability and that x lies between a and b, you can get you can evaluate the integral from a to b of the probability density function f. So that's the recall. You learned this one in calculus 2. The same way, we define the joint density function for a pair of random variables x and y. That is a function f such that the function is non-negative for at every point and integral over whole plane is 1. Once you want to find the probability in over a region D, then you can get it by evaluating the integral, double integral over D of the joint density function. Okay, let's try to solve some problems. Okay, here a function is defined along with a parameter. Now, we find the parameter k, that's the first one, and then we try to evaluate the probability. Okay, it's non-zero, in fact, non-negative only on a small rectangle, and outside the rectangle, the value is 0. So that for the first part, okay, integral over whole plane f can be obtained through integral. Now let's say that region is D, then over D, because outside of D the function is 0. So we have that. Now for this one, we can get it quite easily. The given density function is separable, and that is a rectangle. So we can get the integral separately. Okay, so that is x direction from 0 to 3. Okay, let's write first the double integral from 0 to 2, and that's k and 3x minus x squared, that is 2y minus y squared, and that is now dy and dx. Okay, it's a separable, so k will go out, and x direction integration is from 0 to 3. That is 3x minus x squared dx. And y direction from 0 to 2, and 2y minus y squared and dy. Okay, so there's k times. This one is 3 over 2 x squared, right? Antiderivative, and minus 1/3 x cubed there. And then from 0 to 3, and in y direction, there is y squared minus 1/3 and y cubed there. Y is moving from 0 to 2. Okay. From this one now, and if you try to evaluate this one with x3, there's half 27 minus, okay, that's 27, 1/3 27, so that 27 over 6. And from this one, that is here 4 minus 8 over 3. So that will be 4 over 3. So this product is making 6. So the 6k, that must be 1, right? So from here we can get, and k is 1 over 6. So we found the parameter, and we'll move to second part. Okay, now for the second part, the integral must be, okay, the original region, non-zero region is given in this way. X direction from 0 to 3 and y direction from 0 to 2. Now that's x is less than 2. So we have here the left hand side, y is larger than 1, is half. So that we have here that region, right? Okay, that is now integral. Okay, the probability is integral in x direction is from 0 to 2. In y direction, we have that is 1 and 2. And we already know k is 1 over 6, and x portion is 3x minus from here, okay, that x squared, and now 2y minus y squared, okay. From 1 to 2 is y direction, from 0 to 2 is x direction, okay. Now exactly the same way, we can get it, 1 over 6 can come out, and then now it's separable, so that you can get, already we know it's antiderivative. So here 30 over 2 x squared minus 1/3 x cubed, and now in x direction is from 0 to 2. In y direction, okay, that is y squared minus 1/3 y cubed, and that is from 1 to 2. Okay, you can evaluate this one quite easily, and if you finish the computation, then you'll get that's 10 over 27. Okay. Okay. Now expect the values of x and y. Again, we start with a recall. F is a probability density function of a random variable x. Then its mean is defined in this way. Mu is the integral of x times the probability density function. Again, you learned this one from calculus 2. Similarly, we define the mean in x direction, in y direction. So we say that is x mean, y mean. Really similarly, we define it. Now, mu1 is integral, double integral over the whole plane, x times the joint density function f, and mu2, that's y mean, that is the same as the double integral over R2, y times the joint density function. Okay, so that's the definition. So in a sense, now mu1 is the average of x with the density function, and there's mu2 is average of y with the density function. Like when we try to get x bar, y bar, the center of mass, and that is average along with the density. Now, this average is along with the probability density function, but we don't have here 1 over m. in fact is there, but integration of f is 1, so that we ignored here. Okay, so it's basically the same formula. Okay. Okay, now we'll try to solve a problem. F of xy is defined in this way inside the unit disk. This is value, non-negative, and because these are less than or equal to 1 in modulus, so that this numerator is always non-negative, so that this is a non-negative, and outside the disk, the value is 0. Okay. First one is verify f is a joint density function. Okay. Part A. We already know that f is non-negative. The secondly, integration over whole plane must be 1. Okay, let's do that. Integration over whole R2 plane f. But f is 0 outside the disk. Let's say this disk is D, then it will be same as integral over D of f. Okay? Now D is a polar region, so that we can use polar coordinates. Angle is from 0 to 2 pi, whole circulation, and r is from 0 to 1. Now, the integrand must be expressed as a function of r and theta. Okay, from this one, and x squared plus y squared is r squared, so that numerator will be 4 minus 2r squared. On the bottom, we have 3 pi, and here dA must be changed to be r, dr, d theta. Okay, so this one is theta independent, so that out integral will have 2 pi immediately, and this one, okay, we try to put out and this constant twice 2 over 3 pi, and then integral from 0 to 1, and that is now 2 minus r squared, and r dr. Right? Okay, now from this one we have a pi cancelled, and 4 over 3, and then there is 2r, so it's r squared in its antiderivative. There's r cubed, 1 over 4 r, 1 over r to the 4, and from 0 to 1. So that's 4 over 3, and there's 1 minus 1 over 4, which is 3 over 4. This product must be 1. So the integral of the function and over whole plane is 1 and non-negative, so that it is a joint density function. Okay. Now part B, we want to find the probability when x is non-positive, y is non-negative. Okay. This is a non-zero region of the probability density function. Now x is non-negative and y is non-positive, non-negative. So only this one. Okay. So over this region, we want to find the probability. Okay, let's say that is region, what is the, okay, probably dp. Then we have to get here double integral over dp and f dA, right? Okay, compare with this one, nothing is changed except the angle. This one has from 0 to 2 pi for whole circulation, but now we have to use here from pi over 2 to pi, which is the quarter of a whole region. So we can get it after calculating the whole thing. You will have the answer quarter. Okay. And also, now this one, the density function is only depending on radial component, is angle independent, so that once r is decided, then along whole circle, the value is the same, so that once region angle is 1/4 of original one, then the answer must be a quarter. Okay. Okay. Now let's try to get expected value. Okay. Now, okay, let's try to get mu1 first. mu1 must be double integral over the whole region and x times f dA, right? Okay, again, this is a polar region, so it is from now 0 to 2 pi, and r is from 0 to 1, x is r cosine theta, and then for f we know that is 4 minus 2r squared over 3 pi, and we have here r, okay, and then dr d theta. Okay, this one is separable, and the theta portion and r portion is product, is separable, and that is polar rectangle. Yeah, bottom and top, they are constants. So that, for example, here in theta integral, we have now that is cosine theta, d theta, and remainder part will make r integration. You don't have to worry about r integration because already this one is 0. Cosine theta for whole cycle, halfly positive, halfly negative, so that must be 0. 0 times some number must be 0. Okay, how about mu2? Mu2, rather than x, we have to use y. Y will be in polar coordinate r sine theta. So rather than cosine theta, we are using sine theta. Again, this is a separable. And so that once we try to get this integral along with the sine theta, then again it's 0. So we can conclude mu2 is also 0. It's angle independent and symmetric along the angle, so that the x mean and y mean must be 0. Okay? Okay, that's the end of the section. Thank you.